All right, well, I'm glad everybody's here because this is a rather important day. I have a bunch online. Uh, First up is we have exam 3 coming up, which is scheduled for Thursday of this week. I don't want to shock you. It wasn't nice to have a full spring break, come back refreshed. I said last time I would put that off. Exam 3 is moved to Tuesday, 1 week from today. That way we can cover the whole chapter because I haven't quite finished the last section. And also we can still have a little recovery after the spring break, right? So exam 3 moved to Tuesday, 1 week from today. Later today, I will put up practice problems. Please look for these. Online on D2L. The test is going to cover chapter 7 only, so it's actually only 3 sections, but on the other hand, this is probably going to be the hardest test of the semester because section 7.3 is a pair. We spent our whole lecture on it last time. We're going to spend our whole lecture on it this time also. Chapter 7 only, problems similar to homework as always. Most of them similar to the practice problems. These are hard ones. If you can do these, I think I'm pretty confident you can do the rest of the course. Next time, we're going to spend the whole class in review. Probably a lot of them will be reviewing what okay, but any problems you have out of all chapter 7. So look at these review problems, look at the homework problems, and we'll just do review over all this stuff next time. Today, the homework will just be finish 7.3. All the problems on the UCO supplement. Just the usual thing I've been doing all the homework. So make sure you can do all those, and the test problems will be similar to the problems out of chapter 7. Are there any questions online? You can take your mute off and ask questions if you want. I don't need all this for the test, so we these problems, right? All these things, we can answer your questions next time. 7.3, maybe I better make sure. Right, it is 7.5. I'm sorry, there's 5 sections. 7.5 now on solving trig equations. Any other questions? That's a good one. Okay, so that's it. Today we want to do problems out of 7.5 and finish that section. I know it's been a long time since we looked at this, so we've got to do some review problems first on 7.5. Solving trigonometric equations. So this is really continued, but I'm going to go back to the beginning just for a little review. One, the simplest problem in this is to solve trig function equals a number. But I'm going to do some more complicated problems this time. What do I do if I have an equation trig function equals a number? Here's the strategy. First, get one angle, get a single angle. In other words, if I have 2 theta, a double angle, substitute u equals 2 theta and make it a single angle, right? If I have 1/2 theta, let u equal a half theta and get a single angle. It's 3 theta, substitute 3 theta. Get a single angle by a substitution. Right? Then solve for that single angle on the unit circle. How important the unit circle is? Once you do a lot of these, you can start to visualize what's going on. And I can solve all these problems in my head just by visualizing the unit circle. It is a great tool. Now, go back and apply any restrictions, like a lot of times they'll say, find only angles between 0 and 2 pi, right? And you have to go back and do that. So apply any restrictions and get back the original angle. Get back the original angle in the desired interval, such as using pi over all angles. That's the strategy. You don't have to memorize all these steps. The main one is to memorize, just solve it on the unit circle, right? With a single angle. Okay. Get to the end here. Let's move the camera over. Please ask lots of questions today. This is hard stuff. I think this is the hardest material of the semester. And like I said, the next exam will be easier. The final exam will have some of these again. So here's an example. Suppose I said, solve for theta between 0 and 2 pi. Radians, I think, is the harder case, but it's actually the one you need more in mathematics. Solve for theta within one rotation. The equation, sine of 2 theta equals minus 1/2. Right? Suppose I want to solve that. What do? Oh, look, it's trig function equal a number. I apply my strategy. I'm going to get a single angle. I think you can remember this. Instead of 2 theta, I'm going to let u equal 2 theta to get a single angle. All right? Get in the habit of doing this when solve sine u equals minus 1/2 on the unit circle. So this is A, B, solve on the unit circle for all angles. How do I do that? It's important here, I think, to draw this somewhat accurately. If you draw this in the wrong quadrants or something, you can get wrong answers. You can kind of trick yourself. It doesn't have to be real accurate, but just sort of don't draw it way off because you can get wrong answers. Sine u equal minus 1/2. How do I solve that? Remember this? We did this last time. Well, what I do is I say sine u in the unit circle is the y coordinate, right? This is x and y, and I'm looking for all points y equal minus 1/2. That's a horizontal line, and I try and draw it around here. This is down here. This is -1 because it's a unit distance down here. So the line y equals minus 1/2 is about halfway down. There's all y coordinates minus 1/2 is this horizontal line from algebra and geometry. And then to get sine u equal that number means that I have to have a point on the unit circle. Since this cuts the unit circle, that's why you don't want to draw it down here, right? It goes into the unit circle, it's going to intersect in 2 points, and we observe there's going to be exactly 2 terminal rays. And if you drew this carefully, then you'll notice that there's a symmetry, that what always happens in these figures is this angle is always equal to this angle, right? So how am I going to figure out the angles that this is? If I want this all within one rotation, I'm first going to actually solve for all angles and then throw out the ones that aren't within one rotation. So here's one angle here I can figure out. If I drop the perpendicular on either of these terminal rays to the x-axis, I can make a reference triangle. Remember doing these? And what is the length of this side here? Yeah, it goes down to y equals minus 1/2 here, so the side length must be plus 1/2. And then this side, the hypotenuse here is length 1 because it's a unit circle. And I recognize from memory, if I have side 1/2 and side 1 in the unit circle, the last side has to be square root 3 over 2. The last side is determined by the Pythagorean theorem. We already know from memory that it's square root 3 over 2. This is a 30, 60, 90 triangle. So this must be a 30-degree angle opposite the short side. Rather than writing degrees, since I'm solving for radians, right? When I write theta between 0 and 2 pi, that means write your answer in radians. That's what it means within one rotation. And so this angle must be 30 degrees in radians is pi over 6. Now you always apply symmetry. This one will also be pi over 6 because it also goes down half a unit and has radius 1. So just without any calculation, write pi over 6 also. And now I know exactly what those angles are. Right within one rotation for u, there's this one and there's this one, but that's all I get in one rotation. So I'll write down those ones here. I'll say u can be pi, a straight angle, plus pi over 6. And I have to use my algebra here, right? If I have quotients, I have to put them over a common denominator. So I'll write this as 6 pi over 6 plus pi over 6 gives me 7 pi over 6. Getting off, isn't it? It is off. There we go. So that's one angle. That's this one right here. So theta equals u I'm solving for is 7 pi over 6 is one possibility. And then there's another one though. It's this one all around here. Or I could call it this one, but since I'm looking for positive angles, I'm going to do this one. This angle here is u equals, you could go pi plus pi over 2 plus this one. That's a mess. Why not say 2 pi less pi over 6? Right? Same thing. U equals 2 pi minus pi over 6. Rewrite with a common denominator is 12 pi over 6 minus pi over 6 is 11 pi over 6. And so I'll call this 11 pi over 6. Those aren't my answers. I was looking for theta. I solved for u. So I'll say this is all solutions u. These are all solutions u within one rotation. What are all possible angles u? What are all u that give me those same kind of cosine? These aren't the only answers. What are the other ones? They're all coterminal angles. The only way I can get sine, the y coordinate, is to take these 2 points here, but there's an infinite number of angles that go there, right? I could take this one plus 2 pi plus 2 pi plus 2 pi, any whole multiple plus or minus of 2 pi, a whole rotation. So I have the answers are u equals 7 pi over 6 plus 2 pi times k. We usually write it as 2k pi. Is any k rotations where k represents an integer, right? A number with nothing after the decimal point. 0, 1, minus 1, 2, minus 2, etc. And the other ones are 11 pi over 6 plus 2k pi. And I'll remind you, just for this example, you don't have to write it on paper. K can be 0, 1, minus 1, 2, minus 2, any integer. Infinite number of solutions there, right? So those are all solutions u. But wait a minute, I want theta, and u was equal to 2 theta, so I'll write 2 theta equals that. And now I'll say, what are all solutions theta? How about that? Well, you just divide the equations by 2. Divide this by 2 and get theta equals, you have to divide the whole side. 7 pi over 6 divided by 2 is 7 pi over 12. Plus this divided by 2 is k pi. Or, don't write the word and, that means it has to satisfy both equations. Or you can have, or you just put a comma between them, that's just as good. Theta equals, this divided by 2 is 11 pi over 12. Plus this divided by 2 is k pi. There's all solutions theta. If I ask you for all theta, you'd be finished right here. Alas, I've asked you for theta only between 0 and 2 pi. I solved for all angles theta. And so now we need to reduce it. And so I'll say, which of these angles are actually between 0 and 2 pi? What you do is you start with k equals 0, try letting k get a little bigger and a little smaller, see which angles are between 0 and 2 pi. So if I put k equals 0, I'll get 7 pi over 12 plus nothing. That's k equals 0 in the first list of solutions. These are two lists, both of solutions, two lists of solutions. And right, 2 pi is 24 pi over 12, so this is within 2 pi. If I take 7 pi over 12 plus 1 pi, what do I get? 12 pi over 12 plus 7 pi over 12 is 19 pi over 12. When k equals 1 in the first equation, I get this. This is less than 24 pi over 12. It's also within 2 pi. Now, if I put k equals 2, I've got 2 pi plus a positive angle. That's too big, right? So I can't put k equals 2. I can try k equals minus 1. Well, minus pi plus this is negative. That's too small. So only k equals 0 and 1 works for this first equation. Same thing down here. If I put k equals 0, I've got 11 pi over 12 plus nothing. It's 11 pi over 12. That's k equals 0 in the second equation. If I put k equals 1, I've got 11 pi over 12 plus 12 pi over 12 is 23 pi over 12. I'm just doing quick algebra here. And that's between 0 and 24 pi over 12, 2 pi. So that's good. But if I put k equals 2, I've got 2 pi plus a positive angle. That's too big. If I put k equals minus 1, 11 pi over 12 minus pi is actually negative still, so that doesn't work. That's it. I get 4 solutions. These are the exact solutions. If I ask for solutions, exact solutions, 4 solutions to that. And it's actually harder finding the solutions between 0 and 2 pi than finding all solutions, because you first find all solutions and then reduce it, right? Any questions on that one? That's kind of tricky already, but that was the first and easiest problem, although I'm doing the hardest case of the easiest problem, really. Trig function equals a number. Make sure you have a single angle. Trig function of a single angle equals a number. Solve on a unit circle for all angles. If you're restricted 0 to 2 pi, throw out any extras. Right? All right, well, let's try another one now. Stop me as you have questions, because I know this is a hard section.
What would happen if it wasn't a special angle?
Oh, she's asking what would happen if it wasn't a special angle, if you're online. We're going to do that one next, actually. So you remember this basic outline, but this section just requires practice for exactly that reason. Is there's a lot of cases you just have to think about a little, and you can't memorize all those details. You just have to memorize the basic outline and have done these enough that you can figure that out. So here's another one. This time I'm going to solve again for theta between 0 and 2 pi. Actually, let's solve for all angles. This one, all angles. Tangent theta equals 3. How about that one? And this time it's not a special angle, which was the question. So what are the solutions going to be? If I want exact answers, I'll leave them in terms of inverse trig functions. So let's put exact answers in terms of inverse trig functions. You can see one answer right away, right? Arctangent of 3 is one solution. Right? So, but what you do is the same thing, right? You get a single angle. Well, it's already just a single angle, right? So single angle, check. That's A. Part B, I guess I should have written C over there when I reduced it back to theta. So I should put that on there, I suppose. Put C, all solutions theta. All right, so all solutions theta has the label C back there. B here, I'm going to find on the unit circle. So I sketch this, and like I said, once you've done a bunch of these, you start to be able to visualize this so you can figure it out. But tangent and cotangent are actually the hardest case on these, because what I want now is tangent theta equals 3. But tangent theta isn't x or y. You can't just draw a line to say what are all the points tangent theta equals. In other words, tangent theta is equal to y over x. Right? Oh, so maybe this is 3 over 1, and y is 3 and x is 1. I could have sine of theta is 3 and cosine theta is 1. No, I can't. Why not? Why can't this be the sine and this one be the cosine? Because this is not a point of the unit circle, right? Sine is never equal to 3. Sine and cosine are both numbers between plus and minus 1. I have to rewrite this so it's a point on the unit circle. If I think of this as y over x, I think of this as going over 1 and up 3. 1, 2, 3. I go up to this point way up here somewhere. 1, 3. And sure enough, this is the angle. This angle right here has this tangent. But the point is that on the unit circle, I want this point right here that's on the unit circle. So what I do is I divide these by the root sum squared of them. Square root of 3 squared plus 1 squared, right, is square root of 10. So what I need to do then is divide top and bottom by square root of 10 and write this as 3 over square root of 10 over 1 over square root of 10. And now this can be y, the sine of theta, and this can be x, the cosine of theta, on the unit circle. So there it is. This is the point x, 1 over square root of 10, y, 3 over square root of 10. You can rationalize these and write this as 3 square root of 10 over 10 and square root of 10 over 10. I think let's not do that. This saves writing. In higher mathematics, we often don't rationalize it. At the bitter end, you want to rationalize it to compare with your answer in the back of the solutions manual. All books eventually do that for their answers. The idea is that once they're rationalized, you can look at two numbers. If they look the same, they're equal. If they don't, they're not equal. But in the intermediate steps, let's save some writing and just leave it as square root of 10 on the bottom, right? So there's the point on the unit circle. That's the cosine and the sine of that angle, right? And now I've missed some solutions though. What have I missed for a solution? Just one solution. There's one more point on the circle that has the same ratio y to x. It's the one directly opposite. For tangent and cotangent, the one opposite is always a solution too. It's the point with minus those coordinates. Minus 1 over square root of 10, minus 3 over square root of 10. All right. So I'll say over here, I think this is going off, is it? We got enough visibility. It can be this. Let's see here, I guess it's on there. Or it can be minus 3 over square root of 10 over minus 1 over square root of 10. Minus the top over minus the bottom. And this could be sine of theta. And this could be cosine of theta. So there's different angles, and you can put them in terms of arc sine and arc cosine. Since we started with tangent, I'll put it in terms of arc tangent and say, what are the solutions? Let's move this over. Well, actually, let's first draw it here. One solution when tangent theta equals 3 is always the arc tangent. Maybe it's this one. Theta equals arc tangent of 3. We call that an exact answer. Right? So you can compute it as many decimal places as you want. Is it that one? Maybe it's this one. Maybe it's this one. What is it? Which one is arc? This one or something. What is the arc tangent of 3? Remember, the arc tangent is always an angle between plus and minus 90 degrees, so it's in here. It has to be this one here. It can't be 2 times around and then here. It can't be down to this one. It has to be an angle in here between plus and minus pi over 2 in radians. And there's always only one arc tangent. It's a function, right? So it has to be this one. So there it is, arc tangent of 3. And so by symmetry, this one also is going to be arc tangent of 3. And if I want the second angle, I just take pi plus arc tangent 3. So there's the two angles that I want. Theta equals that, and theta equals pi plus that. Let's move this over a bit and say, therefore, 3 dots mean therefore, solutions are theta equals arc tangent 3 or arc tangent 3 plus pi. And I remember what we did last time. We said, wait a minute, we're not solving for all angles between 0 and 2 pi. This time we're finding all angles whatsoever, right? Maybe I better put this back a little so you can see the unit circle, huh? All right, let's zoom it out a bit. All right, so these are all the angles, this one and this one within one rotation, right? I go around, I hit this terminal ray, hit this terminal ray, and then I'm back. It's only those two angles. But remember, any coterminal angles will have the same trig values, and so all the other angles that have these terminal rays should look directly opposite by drawing. Will be the coterminal angle. So what I can do is add any whole rotations, k times 2 pi gives me k rotations, where k is any integer, right? The integers are 0, 1, minus 1, 2, minus 2, and on forever. All those, I won't usually write this anymore, I've written it. But k times 2 pi, same thing here, plus k times 2 pi. So this is actually the correct answers, but I can write that simpler. So on your paper, if you leave it like that, I'll give you full credit because that's actually right. But how can I write this simpler? Here's what happens if these angles are directly opposite each other like this. Instead of saying this one plus a whole rotation plus a whole rotation, and then this one plus a whole rotation, a whole rotation, and so on. I can say this one plus a half rotation plus a half rotation plus a half rotation gives me the same set of angles. Better, or let's say simpler again, we simply write either one of those angles. Let's use arctangent 3 plus k half rotations, k pi. There's all the solutions where you don't have to write this list of integers if you don't want to. It's assumed when you write k. Okay? So there's all solutions to this thing exactly. For a non-special angle, you just leave it in terms of the inverse trig function. Now we'll slowly set this. These are the exact answers. You can run that for any number of digits you need. For approximate answers, if I say approximate it to 2 decimal places, what can I do? I run it on the calculator, right? To do arctangent 3, and again, I can't write infinite number of answers. So let's say for k theta between 0 and 2 pi, I just have these two answers. I need arctangent of 3 and arctangent of 3 plus pi for the, then I say arctangent of 3 can be run on the calculator. And then you take the first answer and add pi to get the second answer. What I do is I can push these keys. Move this over now. I think the suit is going to be white by the time I finish. All right. So you push second tangent because the second button is a colored button, and above tangent in the same color is inverse tangent or arctangent. You push that to get arctangent. Then you can push 3, and parentheses automatically inserted on newer calculators. Usually it puts 2 parentheses here, and you don't need to push an additional button. But you can, if on my old calculator here, I have to push a closing parenthesis to close it. And then you push enter to evaluate it. Arctangent 3, that's it. That'll give me the first angle. And what do I get on there? Make sure you're, since we're looking for radians, we want radians mode. If you're in radians mode, you should get this answer. Second tangent 1.249 0.45, etc. And if I want 2 decimal places, I look, that means 2 places right at the decimal point. So I'm gonna stop here, and if this number is 5 or greater, I'll round it up. So I'll say this is approximately 1.25. Okay, so there's one answer. And then the other one, what I want is arctangent plus plus pi, right? So that's one, and then the other one, I'll push second minus on the TI 83 or 84, because up above here it says and. That brings up the last number that was displayed on the calculator. I don't have to retype these all in, plus pi. This will give me back my last angle. And then just push plus, and I can push second caret, and because above the caret key is pi. Other calculators have the same thing. You just push second some other button to get pi, second some other button to get answer. And so this is answer on the screen plus pi to lots of digits, all it will carry. You get lots of decimal places. And in fact, actually, if on most calculators, if it's the first thing in here, you don't even have to do this. You can just push, you can omit this and just push plus second pi, and it will automatically put the answer up. So that's what I'm going to do. I'm just going to push plus second pi, and I get an answer of 4.3906, etc., which rounded to 2 decimal places is 4.39. Now the next digit is less than 5, so I just call it 4.39. Don't round it up. So here's my 2 answers on that one. Comments on that one? So tangent is harder. You have to write as a quotient, and then divide top and bottom by the root sum square to find out what angle, what you get out of there. And you can solve this with arctangent and arctangent plus pi. All right. So that's the first step. One is solving trig function equals a number. Now we want to step it up a little. These are not too much harder. It's just also algebra plus doing the same kind of thing. To solve a trig equation, which is a times a trig function plus b equals 0. What do I do to solve that? I just treat it like it's an algebra equation. A times u plus b equals 0. How would I solve au plus b equals 0? I subtract b and divide by a, and I get u equals minus b over a, right? I do the same thing here. I subtract b from this one and write equivalently. Right. I don't even need an a, b on this one. It's just right. Trig function, just like I was solving for u here, equals minus b over a, right? And now I have trig function equal a number. So I go to method 1. That's it. I guess I could write a and b. A, write it as trig function equals minus b over a. B, apply trig function equals a number. Or apply method 1. So it's not much harder than the last one, but there are some problems like that. For example, suppose I said solve 3 times secant theta plus 2 plus 5 equals 0 for theta between 0 and 2 pi. Suppose I give you that problem. What would you do? A trig function plus b equals 0. You just immediately write, for step A, right? Subtract 5 and divide by 3 and get secant theta equals minus 5/3. Right? Now, how do I solve that? We've done tangent, we've done sine. What about a secant? Well, when you come to secant or cosecant, it's best to rewrite it as the reciprocal. So I didn't put this on the instructions because this is one of those details. You don't want to memorize a whole long list of things. The idea is from previous examples, you're supposed to remember, you can also write this as reciprocal of the left cosine equals reciprocal of the right minus 3/5. There it is. So I solve cosine theta equals minus 3/5. Now, what if I got cosine theta equals minus 5/3 instead? Suppose this was the problem. What would I say immediately? I'd say no solution, right? Cosine is a number between plus and minus 1. This is less than minus 1. There's no solution. So in some of these problems, there's just no solution. It's easy to write those. This one, however, there are solutions because it's a number between plus and minus 1. So I can do this then. Again, if it's a sine or a cosine, then it's an x or y coordinate. Cosine is x. I just draw the unit circle. So P, now I go to method 1, right? Trig function equal a number. And so it's just an AB, right? Rewrite it as trig function equal a number, solve it as trig function equal a number. Simple as that, right? So draw the unit circle. This time I want all x coordinates equal minus 3/5. That's a vertical line. So I'll go pretty accurately. I don't want to draw it over here. I'll probably make a mistake. 1, 2, 3, 4, 5. Say, well, it's somewhere around here. Doesn't have to be real exact, but just in these two quadrants and sort of in the right place, and say, I can see since it cuts the circle, right? It's not over as far as minus 1. If there's going to be exactly 2 points in the unit circle that have that x coordinate. Therefore, exactly 2 terminal rays that can give me that x coordinate. This one here, this one here. And solving for theta between 0 and 2 pi, I notice that there's this angle and there's this angle. What are those angles? One of them is immediately the inverse cosine, right? You can write it that way. And why I'll use the inverse cosine because this isn't coming from a special angle. A special angle, I want to draw my special triangle. But for a general angle, I'll say, well, one answer is the inverse cosine of 3/5. That's one possibility for theta. Is it that angle? Maybe it's this one. How do I know? Or maybe it's this one. This is where you have to remember the arc cosine, there's only one answer because it's a function, is the unique angle, it's one of these terminal rays between 0 and pi, 0 and 1, and one straight angle. So it must be this one. I drew it in the right place. That being the case, by symmetry, this other angle has to be the same. This also has to be the arc cosine of 3/5. Which means that the angle I want the angle between 0 and 2 pi. I don't want to take minus arc cosine of 3/5. I want to take this one, which is what? 2 pi back up arc cosine. So the other angle here that I want is theta equals the whole rotation less arc cosine 3/5. If you want exact answers, that's it. You're done. If you want approximate answers, then you run those in the calculator with the inverse cosine and round. Okay. Looking for, here we go. Here's another one. Suppose I said solve 2 sine 2 theta equals square root 3. Again, solve for this exactly. Solve for theta. I'll write it the same as your home instructions. Solve exactly on, I'm off the picture here, am I not? Sorry. Tell me when I do that on mine. Solve exactly on the interval 0, pi. What does this notation mean? This means whatever variable you have, theta in this case, has to be between these two angles. The square bracket means include the endpoint. The round bracket means don't include the endpoint. So this time we don't include 2 pi. That's what that means. Interval notation instead of inequality notation. How do I solve this one? It's not trig function equals a number, but you can think of this as a trig function plus b equals 0, except I've already subtracted the square root of 3 over. All I have to do is write equivalently, dividing this by 2, and I get sine 2 theta equals square root 3 over 2. There it is. On this one, I recognize that this number comes from a special angle, so I'm going to be able to solve this one exactly, right? Unless I asked for that. But once again, it's not a single angle, so I'm going back to now you apply method 1, right? Once you rewrite it as trig function equals a number, you go back to method 1. So get trig function equal a number, case 2 here. This time just by dividing by 2 is easier. B, go back to method 1 for trig function equal a number. So for method 1, you get a single angle, you let u equal 2 theta. You get sine u equals square root of 3 over 2. Once you have that, right, you can solve it on the unit single angle, you can solve it on the unit circle for u. So let's try that. Again, you do a lot of these, you can do this in your head, but sine is the y coordinate. So y coordinate equals square root of 3 over 2 to avoid mistakes. Remember, square root of 3 over 2 is pretty big. It's like 0.87, I think. It's way up here. Right? These are all points on the plane y equals square root of 3 over 2. And there's then, I observe, since it's less than 1, it's going to cut the unit circle at 2 points. And I'll have exactly 2 terminal rays, one here and one here. And if you draw these carefully, you notice there's a symmetry. This angle and this angle are equal, right? Congruent. So what am I going to find for those angles? Once again, I can say, well, one solution is arc sine of square root of 3 over 2 for this, but I don't want to write arc sine. Why not? Write arc sine there. I can, and it's true, but you want to solve this exactly. What you do is drop the perpendicular and say, if this goes up to square root of 3 over 2, this side length is square root of 3 over 2. This side is 1 because it's a unit circle. Oh, it's a 30, 60, 90 triangle. This must be pi over 3 since it's opposite the longer leg. By the same token, then symmetry always applies. This must be pi over 3. Now I observe that there's 2 solutions. U within one rotation. Let's see what the solutions for U are. We'll say one solution is this angle here, right? U equals pi over 3. Another one is this one. Well, let's see what that is. So I take pi back up pi over 3. Right, straight angle less pi over 3. Well, 1 pi minus a third pi is 2/3 pi, right? So that's the other angle. But I'm not done, all right? If the original problem was 2 sine u equals square root of 3, I'd be done. These would be all angles within one rotation for u. But at last, I started with a multiple angle. When I have a multiple angle, I have to go back and find all angles and throw out the extras. So keep that in mind. If it just starts as 2 sine u, then I'm done here. These are all the angles within one rotation. But I need to find all the angles, so I'm going to add plus 2k pi, k rotations, plus 2k pi to each. You can't combine them like with the tangent since they're not opposite each other. And we'll say these are all solutions for u, arbitrary number of rotations, right? And I can deduce all solutions theta, and then I'll throw out the extra ones. But when you have a multiple angle, you have to find a good way to do it is to find all angles and then throw out the extras. Otherwise, what you have to do is you say, well, u equals 2 theta. So I'll find all u within 2 rotations. And then that'll give me all theta within 1 rotation. That's awkward. So usually instead we just find all angles and throw out the extras. You can do it either way you like though. So here's this one, all solutions u, but u is 2 theta. So I divide that by 2 and get theta equals here. You divide the whole side. Pi over 3 divided by 2 is pi over 6. 2k pi divided by 2 is k pi. Or we can have a second case, divide this one by 2 and get pi over 3. Divide this by 2 and get k pi. So there's all solutions theta. Now finally, I can reduce this to all theta between 0 and 2 pi. This is what I wanted in the beginning. By considering k equals 0, k a little less, k a little bigger until I get too big and too small. So if I put k equals 0 in the first equation, I get pi over 6 plus nothing is pi over 6. If I put k equals 1, pi over 6 plus pi is 7 pi over 6. I'm doing it faster now. Pi over 6 plus 2 pi is bigger than 2 pi. That's too big. If I put k equals minus 1, pi over 6 minus pi is negative. That's too small. So I'm done. K equals 0, k equals 1 in the first equation. Second equation. Suppose I put k equals 0, I get pi over 3. Suppose I put k equals 1, I get pi over 3 plus pi is 4 pi over 3. If I put k equals 2, it's 2 pi plus something. That's bigger than 2 pi. It's too big, right? If I put k equals minus 1, it's pi over 3 minus pi. That's negative. That's no good. So there's 4 answers here to this one. There they are. Okay? When you want to solve it, when you can solve it exactly, you want to make the triangle here. When you want to solve it with a multiple angle, you're going to find all solutions and then throw out the extra ones. They're solving a times the trig function plus b equals 0. You just solve for the trig function and go back to method 1. It's not much harder. Okay. Stepping it up again. We can now say part 3 is to solve a times the trig function squared plus b times the trig function plus c equals 0. Suppose I can write a trig equation in that form. This is called a quadratic equation in a trig function. You know to recognize it because the square is in here. If you see something like that, we can still solve it, but it's a little more detailed. We did one of these last time, but not in this much detail. I remind you, what do? First thing you do is let u equal the trig function. So A, let u equal the trig function to get a quadratic equation. Because now what you get is a times u squared plus b times u plus c equals 0. Important to get 0 on the right-hand side. If it's not equal 0, then subtract over to make it 0. Because that's how you solve the quadratic equation. Remember from algebra, this is why algebra is a prerequisite, is I now expect you to remember these things. Solve this for u. Solve the quadratic equation for u, either by factoring or by the quadratic formula. You use either one you want, except factoring sometimes it's hard to guess the factors, so sometimes it doesn't work, but when it does work, it's usually faster. Quadratic equation, quadratic formula always works, but it's longer sometimes. So solve a quadratic equation like you did in algebra by factoring or the quadratic formula. There's also completing the square. That's same answers as quadratic formula, it just takes longer, so I won't do that method. By factoring or the quadratic formula. First one's faster, second one's always works. I see, always make this work. And then C, once you have solved that by quadratic equation or factoring, you've got u equal a number, right? Well, u is a trig function, so you go back to method one, because now all these solutions here are trig function equals a number. Solve trig function equals a number by method one. Well, I told you, it's like the house that Jack built, it builds on itself, right? And then to do this third method, you apply the quadratic formula or factoring, and you get sometimes with the second method, sometimes the u equals, maybe I should say, or method two. If you use factoring, you may get an a equals b equals 0. But it reduces you to method one or method two. If you go to method two, then you reduce that one to method one, and you solve all these things, right? There it is. Let's do this example then. Suppose I had, this is number 8A on your homework. So when you go to try the homework, you can look at this and you get stuck to know what to do. By the way, all my office hours are again in person. If you want to come into the classrooms listed on your syllabus, I'll be there in MCS 103, for instance, on Mondays and Wednesdays for office hours. I was there yesterday, for instance. And 113, MCS 113, just down at the end of the hall here on Tuesdays and Thursdays, I'll be in there if you want to come in person. And then I'll also turn that online, so you can meet me online and I'll write on the blackboard while I'm in those classrooms. Or you can meet me in person now in those classrooms if you want. And don't forget, if you're stuck on these things that's outside when I'm not here or something, the tutors at the end of the hall, MCS 100, they do free tutoring. They're paid by the department. You can come in and talk to them. They tutor all the way through calculus, so they can help you with trig. Just go in there and sit and work on your homework. Whenever you're stuck, just wave your hand. And it's also a computer terminal room, but the one who has tutor written on their tag will come over and help you. Sometimes there's more than one. They're paid to do that. So, take advantage of the free resources. You're just down at the end of the hall there, right? So you get all your homework done that way. Tangent squared theta, the homework thing says x, but I want to use x for my cosine coordinate. So I'll say tangent squared theta, and I'll probably make the test this way. I'll use theta as x plus 3 tangent theta minus 3 equals 0. Suppose I want to solve this approximately. Round to 2 decimal places. Or theta between 0 and 2 pi. Since it's a single angle, I only need, I don't need to solve for all angles and throw out the extras. It's just when I have like a double angle or half angle and not a single angle, I need to find all solutions and then throw out the ones I can't do. So this one, I'll just solve it straight on the unit circle, not have to throw anything out. How do I solve this problem here? How about well, the first thing you do in this one is when you see a quadratic equation of trig functions, you make the substitution, u equals tangent theta, and make it a quadratic equation, right? This makes this equivalently, when equivalent means it has the same solution set, u squared plus 3u minus 3 equals 0. So you get that equivalent quadratic equation, right? You solve that by algebra, either completing the square or factoring. Which method should I use is always a good question. Usually you try factoring first, and if you have difficulty, use the quadratic formula. It's just, if it's easy, you can factoring. But I'll tell you something, this one, the quadratic formula doesn't work, or the factoring is not a good idea. Why is factoring not a good idea? Let me rewrite the problem for the people online. U squared plus 3u minus 3 equals 0. Where u is tangent theta. Why would I have difficulty factoring that? Doesn't it factor? It does. It always factors, right? It factors as 1 times u blank u plus blank u plus blank. If I try factoring equals 0, the lead coefficient in this And if these are integer coefficients, numbers with that, nothing after the decimal point, maybe integers will go in these blanks. When do integers go in the blanks? They go in the blanks if b squared minus 4ac is a square. Well, if and only if, because what happens is the quadratic formula tells you that if this isn't a perfect square, you won't get integers in the blanks. So we compute this. You don't have to compute this. You just try and fill in the blanks. Say, can I put in the blank something? I need 1 and 1 here to make this times this give me the 1u squared. And then so the product here has to equal 1. And the product here has to be -3, right? Because this times this is going to have to give me the -3. Then this times this plus this times this in the FOIL will give me the 3u. Product equals. But I have to put in here, and I can never guess what goes in the blanks on these. It'd be very difficult. Because, right, I can try -3 here and 1 here, and let's see, u squared minus 3u plus u is minus 2u. I can't make that work. Well, maybe minus 1 here. So u squared plus 3u minus u is plus 2u. That's not right, -3. I can't make it work no matter what numbers I put in there. So I give up and try the quadratic formula, but here's how I could have told ahead of time this wouldn't work if you want to do this. Usually you just try it and see if it works. But b squared minus 4ac is 3 squared minus 4 times a is 1 times c is -1. Again, thinking of this as a, b, and c. This one comes out to be 9 plus, oops, wait a minute, 4ac, yeah, is 9 plus 12 is 21. That's not a square. If this is not a square, then it's gonna be very difficult to figure out what goes in the blanks. What goes in there will have the square root of 21 in it is what's gonna happen. And so I have to guess something with square root of 21, and I probably won't be able to guess it. So I'm gonna give up on this, either by trying it, seeing it doesn't work after a few tries, or by noticing this isn't a square. You can prove that it won't be easy numbers that go in the blanks. So instead, I'll go to the quadratic formula. So when factoring doesn't work, the quadratic formula always works. And it says this, u is equal to, you have to memorize this for exam. If you don't remember from algebra, rememorize it. Minus b plus or minus square root b squared minus 4ac all over 2a is always the solutions. And remember what can happen with this. This is why this method is, this case is trickier when you have quadratic. This can have no solution, or it can have one solution, or it can have two solutions. Remember that from algebra? When does it have no solution? Want to remember? No solution if b squared minus 4ac is negative, because you get square root of a negative number. That tells you that there's no real number solutions. There is actually imaginary solutions, but we aren't interested in imaginary trigonometry. So, all right. No solution if b squared minus 4ac is negative. See how important this is? It tells you if you can factor and guess with whole numbers and integers. It tells you if there's no solution. If there's exactly one solution to this, you recall, if b squared minus 4ac is equal to 0, because then you get minus b plus or minus square root 0 is the same whether you put plus or minus, there's one solution, right? And then there's two solutions. If b squared minus 4ac is bigger than 0, because there's one for the plus and one for the minus with a non-zero number here. So that's the quadratic formula. You can get 0, 1, or 2 solutions for u. And let's see what we get here. We've already computed b squared minus 4ac up here. Here's the advantage to computing this. You have it in the next step when you need it. Minus b is minus 3. Plus or minus square root 21, we already computed for b squared minus 4ac. All over 2a is 2 times 1. So there's the solutions. U equals minus 3 plus or minus square root 21 over 2. Now you see why I couldn't guess what goes in the blanks. Guess what goes in the blanks? It's minus these numbers. If you put blank, if you put, take out the lead coefficient here, 1, and put blank u minus blank, 1u minus blank, 1u minus blank, what goes in here are precisely these two numbers. U minus one of the solutions to quadratic formula and u minus the other one. And so how was I ever going to guess to put in these blanks minus 3 plus square root 21 over 2, and minus 3 minus square root 21 over 2, right? So that's why you go to quadratic formula when factoring doesn't work with whole numbers. Well, that's what I do. When I have a quadratic equation in a trig function, I rewrite it as AU squared plus BU plus C equals 0. Solve it by factoring the quadratic formula. Now U is a trig function. In this case, right, it was tangent. So I have trig function equals a number. So I'll say equivalently has the same solution set as this is U equals. U equals is the same as tangent equals. So tangent theta equals minus 3 plus square root 21 over 2. Or tangent theta equals minus 3 minus square root 21 over 2. So it breaks up into two cases because the quadratic formula had two solutions. Right? U equals this and U equals this. Makes it tangent theta. But now look, I have trig function equals a number, or trig function equals a number. I go back to method 1, right? I can solve it on the unit circle. Each one. I have to do two different unit circles now. One for this one for this one. Right? So how do I solve this one? Here's the unit circle. What's one solution to this immediately? By the way, maybe it doesn't have a solution, right? If I said if I put cosine theta equals -2, there's no solution because cosine has to be between plus and minus 1. Maybe this has no solution, right? It actually does. Tangent theta can be equal to any number. Remember, its graph, it looks like this, and then it repeats over and over. All right, so tangent theta can take on any number. Tangent theta equals a number always has a solution, right? So don't say there's no solution to a tangent. Tangent equals a number. Well, this is a positive number, right? This is where the drawing comes in. -3 is not as negative as square root 21. Square root 21 is bigger than 3, right? 4 squared is 16. This is bigger than 4. So -3 plus a number bigger than 4 is positive. Over 2, a positive number is a positive number. So it's tangent theta equals a positive number. I'm going to have some angle in this area over here. I don't know exactly where to draw it, but I don't draw it down here. Why not? What I have here is if I have tangent theta equals a positive number, it's an angle in the, and one solution is theta equals arctangent that number, -3 plus square root 21 over 2. And this, since it's arctangent of a positive number, it's in the first quadrant. Arctangent is always an angle between plus and minus 90 degrees. If the argument is negative, it's a negative angle. If the argument is positive, it's a positive angle. So you draw it in quadrant 1 because this is a positive angle. That might not be in a really accurate place, but I know it's in the first quadrant. That's the key point. Right? So that's one solution to this problem. All right. What are all solutions between 0 and 2 pi again? Well, there's another solution. Remember, tangent, cotangent, the opposite angle is always good. And if this is arctangent, then the opposite angle has this arctangent. And so I can have this angle, which is pi plus that. Theta equals pi plus arctangent. -3 plus square root 21 all over 2. So there's going to be two solutions to that one. And since these are not special angles, I just run them on the calculator. And I'll say the first angle, arctangent, I can just get by pushing those same buttons as before. Second tangent, when it's in radians mode. Oops, hold on. Second tangent. And I need parentheses for this. The calculator, you need to either have a long bar or put parentheses around it so it doesn't divide by 2 last. -3. Oh. parentheses, -3 plus, so this could be difficult to enter, square root 21, close, divided by 2. And I get this number, 0.6694, blah, blah, blah. The 2 digits, all right, the squiggly equals, meaning approximately equal to 0.67, right? The third digit is bigger than or equal to 5, so I round it up. Now, how about this one? I don't want to use 0.67. That added to pi may not round right, so I carry all these. Again, to do this, I can use the second answer key, or I can just use plus pi. So I push on the calculator plus second pi, caret for pi, enter, and it will take the last angle I add up there and add pi to it. So let's try that. Then I don't have to maybe fat finger this thing after. It's so hard to get this complicated expression in there right. So I'll push plus second caret to add pi and get 3.8109. That carries all the digits that the calculator can display. Blah, blah, blah. Rounds to about 3.81. So hopefully that's what it says in the handout here. Again, the answers are in the back, so check your answers as you go. I should get 2 of these answers. They're 0.67 and 3.81 back here. It's down, I suppose. So I shouldn't say all the answers. Some of the answers are back here, I should say. Let's see. Yeah, 0.67 and 3.81. There we go. And actually, your answer key on this one is incorrect because it didn't do the second case here. So there's 2 answers corresponding to -3 plus square root of 21 over 2. But I've got 2 more solutions here also, right? Here, this angle is negative, right? Because it's a negative number minus a positive. The top is negative. The bottom is positive. Negative over positive makes the whole thing negative. So this is tangent theta equals a negative number. I don't know exactly where that angle is, but I do know that there's one angle, the arctangent, that satisfies this, right? Tangent theta equals a number, always has a solution. For tangent and cotangent, that's true. So there's some angle down here. That's the arctangent. This time I know to draw it down here because it's the arctangent of a negative angle. It's always in this quadrant. Arctangent of -3 minus square root of 21 over 2, and I can run it on the calculator. Get it right here. Arctangent, parenthesis, -3 minus square root 1, close again, divided by 2. These are complicated expressions. And I get minus 1.31. To a certain extent, use your sanity check and say, does that number seem about right? If you get minus 100, it's not, right? Arctangent should be between 0 and negative pi over 2. So minus 1.31, that rounds off to 2 decimal places. You don't have to use squiggly equals. I will, but just to indicate I've rounded it. All right, and so there's another answer. Except, oh, wait a minute, that's not right. I want angles between 0 and 2 pi. I should have put this up here. Way back at the beginning, put theta between 0 and 2 pi. Right. Oh, yeah, I did. Yeah, I said solve approximately. I did write it. Okay. So there's another answer that's not in your answer sheet, except it's negative. What am I going to do with a negative angle? It's supposed to be between 0 and 2 pi. Well, maybe I better not box that, huh? What you do is you say there is corresponding to this angle, a positive angle between 0 and 1 rotation. It's this one. This is the angle arctangent plus 2 pi, right? You take the negative angle plus 2 pi, a whole rotation. So the other two answers, if I can stay on the screen here, I hope. This answer is theta equals not arctangent of -3 minus square root 21 over 2. That's not between 0 and 2 pi, but that plus 2 pi. That'll be that direction. And then also, always the opposite angles. Still up here just barely. The opposite angle on tangent is always a solution too. So that's the angle. One of them is the arctangent always. The other one is opposite that one. That's plus pi. So I take theta equals this arctangent I just computed. I add pi to get the opposite angle. That's positive. And I add 2 pi to get the same angle between the same direction between 0 and 2 pi. And these are my other two answers. And I've already wrote those out here, I think. Let's see. So if I add 2 pi, if I add pi to that, let's try just to make sure I get this right, plus pi, and I get 1.82, 1.83. So 1.83, and this one should come out to be 4.97. You run it in the calculator. There you go. All four solutions to this difficult problem. Okay, let me put one last one here just quickly. We'll try and go through the technique again without doing as much detail. Find my page again. The last problem. Again, bring some questions for next time. We'll take on the practice problems I put online, and also all the problems in this section are important. Suppose I did this one. This is an interesting one here. Suppose I was solving 4 cosine squared theta at theta plus 5 cosine theta equals 6. Suppose I had to solve this one. What do? This is a quadratic equation in cosine theta, so I let u equal cosine theta. And I write 4u squared plus 5u equals 6. And I notice there's something wrong immediately. What is it? What's wrong with it? I need to get 0 on the right-hand side to apply either of my techniques. Either factoring or the quadratic formula requires 0 on the right-hand side. So I'll rewrite it like this. Now it's a quadratic equation. AU squared plus BU plus C equals 0. I can apply the quadratic formula, but in this case, I can also factor, right? I can factor this, and since I'm out of time, I'll just do it quickly. Blank U plus blank, blank U plus blank, and try and figure whole numbers. Maybe we'll go on the solution. And this time it will work because B squared minus 4AC is 121 if you work it out as a perfect square of 11. Since B squared minus 4AC is a square this time, there will be whole numbers, integers that go on the blank. And what goes in here, if I remember right, is 2 and 2, I think. And no, it's 4 and 1. It's 4 and 1. You have to just try all the combinations with factoring. And then 2 and minus 3. And you just FOIL and check. This time this is 4u squared. This time this is 8u. Plus this time this is minus 3u is 5u. There you go. And this time this is minus 6. So that's the way it factors. You just fill in the blanks with whole numbers till you make it work. Now, what you do is you say by the zero product property, if you rewrite this, 4u minus 3 times u plus 2 equals 0. The zero product property in factoring says if a product is 0, either this factor is 0 or this factor is 0. So you have two cases, 4u minus 3 equals 0, or u plus 2 equals 0. Zero product property. Now I go to method 2 because really this is 4 cosine theta. U is cosine theta minus 3 equals 0. Or cosine theta plus 2 equals 0. It's a linear equation in trig function. Go to method 2. I can add 3 and divide by 4. I've got cosine theta equals 3 3/4. Or on this one, x subtract 2 and get cosine theta equals -2. Trig function equals a number, right? Trig function equals a number I can solve on the unit circle, right? Actually, I only have one of these to solve. Why do I only have to solve one of these? Yeah, cosine is the number between plus and -1. This one has no solution. Can't make it -2, so I actually only need the first one. And I solve this one on the unit circle. I solve on the unit circle, cosine theta equals 3/4, is x coordinate equals 3/4. So x coordinate is a vertical line. I take all x coordinates at 3/4. I'll get two angles, and since I'm out of time, I'll just draw this real quick and say, those two angles, one of them is arc cosine of 3/4. That's this one that's between 0 and 2 pi, right? And the other one is 2 pi back up that. So this angle is 2 pi left arc cosine of 3/4. So then you can calculate on the calculator what those are. We're out of time, so try all those problems, and I'll see you next time. Best wishes to everybody on the probably the most difficult section of the book. Don't let it scare you. It'll get easier after this. Thank you for coming in today.